Okay, in this video, we are going to go through some sigma notation. That Greek letter at the green at the top of my screen is the Greek letter sigma. It looks kind of like an E, but hopefully it also looks a little bit like an S. That is what it became, and it also stands for sum. So it is a quick way of writing the sum of multiple things. As a way of showing you what that means, I'm just going to jump into that first example, which reads, let me turn on my screen here. Oh, there we go. Which reads the sum, that's how I read it, from k equals 1 to 4 of 2 to the k. So we are summing up all things which look like this when k equals 1, 2, 3, and our last one is when k equals 4. For those of you who have taken some computer programming, looks a little bit like a while loop or a for loop or something like that. So again, what this really means is we are adding 2 to the k equals 1, and then we iterate. So we go up to 2 squared, we go up to 2 cubed, and finally we have a 2 to the 4th. Need to pause and send something to. Okay, and that's what this all stands for. We can do the same thing again with this next one, although we can't be as specific. We're starting again at k equals 1. We don't have to start at k equals 1. We are ending ambiguously at n, and this time we're doing k squared. So this should equal 1 squared plus 2 squared plus 3 squared plus, and I'm going to hit the dot, dot, dot. We're going to end when we reach n squared. If n were 1, we kind of went a little bit overboard and too far. If n were 4, then it would have been easier just to write in 4 squared, but this is pretty good. Shows us what we're doing. Next up, we've got the sum from k starting at 1, k ending when we get to n, of k factorial over k plus 1. Well, all the terms, the things separated by an addition sign, will look like 1 factorial over 1 plus 1, 2, plus 2 factorial over 3, plus 3 factorial over 4, plus a dot, 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 n factorial over n plus 1. So that's it. Again, like normal in algebra, we learn how to do things, then we learn how to do them backwards. So this time we are going to write this as a sigma. Express each sum using sigma notation. So this is sigma starting at 1, ending at 100, and we just have the value of k. Now, that being said, this is the answer that I would expect. However, there are an infinite number of correct answers which you could alternatively put. For example, you could put k equals 0. Think about where it would end, therefore. And now I'm just going to do a k plus 1. Technically, the parentheses are required, so if you don't think it's sigma of k plus 1, but a lot of times we just leave them out and kind of imply them there. Again, you could start k anywhere. You could start k at 72 if you wanted to. You would just subtract 71 from each term. Okay, so all the same there. Next up, we have this thing which looks like 1/3, 1/9, 1/27, etc., etc. So that seems like a sequence that we dealt with in our last class. I'm going to start K equals, what do you think? I think K equals 0 is going to make more sense. And because what I'm doing here is I am really taking 3 to the negative K. Okay. And we end when when we're taking 3 to the n minus 1, 1 over 3 to the n minus 1. So I'm just going to put an n minus 1 there. And I think that that's good. Okay, moving on. Finding the sum of a sequence. Okay, so there are these properties which I really feel that you should understand, and these formulas, which, well, the first one really is that first property. The second one is Euler's formula. No, it's, yeah, it is. It's Euler's formula. The other two, that k squared and that k cubed, are kind of confusing looking formulas. I prove them in another video, which I have already published. So if you want to see some proofs of that, you can. Let's take a look at what these things mean, starting with that first one. So for example, if I had the sum of a bunch of stuff, like all the even numbers, for example, like I did the sum from k equals 1 to 100 of 2k. Something like that. There it is, of 2k. So that would really equal 2 plus 4 plus 6 plus dot, dot, dot. My last one would be plus 200. But it's the same thing as saying 2 times the sum from k equals 1 to 100 of just normal k. Well, that would equal 2 times 1 plus 2 plus 3 plus dot, 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 up to 100. And yeah, those two things seem equivalent. So basically saying we can take out that constant multiplier. Next, if the argument of sigma, by which I mean what is inside sigma here, I think you guys can, no, probably can't see that screen. Probably can see this one. What's inside these parentheses here is a sum. You can split it up into two different sigmas. So if, for example, I had the sum from k equals 1 to 10 of k plus 3, I could split it up into the sum from k equals 1 to 10 of k plus the sum from k equals 1 to 10 of 3. Okay. The next one really is the same one. If you can do it with sums, you can do it with differences. And the last one is a little bit interesting. It's about changing those limits of the sum and saying, okay, well, we don't have to go from 1 to 100. If someone were to say something like, what is the sum from k equals 20 to 100 of, I don't know, k squared, then I could say that is equal to the sum from k equals 1 to 100 of k squared minus the sum, and you have to be a little careful here, from k equals 1 to 19 of k squared. So we're kind of subtracting out all the ones that we didn't need to do our original thing. You might be wondering why we need something like that. Well, if we look down at those different formulas, they all go from 1 to n. So if they wanted to do this, I could use that formula to find this one and that one and just subtract. Let's play a little bit and see how these work. Find the sum of each sequence. So the next problem is I have the sum from k equals 1 to 20 of 3. Well, when k equals 1, 3 equals 3. When k equals 2, 3 still equals 3. In fact, 3 equals 3 every time. This is really equal to 3 plus 3 plus 3. Well, how many of these 3's do I have? I've got 20 of them. By the way, how did I come up with 20? Obviously, it's written right there. But what I generally do is I take this, I subtract that, and then I add 1. So I have 23's. My answer is really 60. The next one I can solve in a few different ways, but I'm going to go right ahead and tell you my favorite way. This is something called Euler's method. It comes with a little story. So it works for linear ones, for ones which kind of fit that mx plus b thing. So the story goes like this. Euler was a young lad in like 3rd grade or something. And his teacher came in, and the way the story goes, the teacher came in one day hungover, not wanting to teach, not wanting to be bothered, not wanting to do any of the little things that involve dealing with 3rd graders. So the teacher hatched the scheme, said, hey, look, this is what you guys are doing today. You are going to add all the numbers from 1 to 100, figuring this will take those 3rd graders like hours. And once they do, they'll probably have mistakes. The first 2 people who do it will undoubtedly not have the same answer. She can ask them to go back and check their work and gain even more time that way. Well, Euler wrote the numbers 1 through 50, and then below it, he wrote the numbers 51, right under the 50, back through 100. So the 100 ended up under the 1. And he looked and he said, oh, okay, well, 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. And he looked and he saw how many groups of 101 he had. That's me pausing for you to answer. He had 50 of them. So he had 50 groups of 101. 50 times 101 is 5,050. He's done. Handed it in, got yelled at by the teacher, who, I don't think bothered to figure out what the answer was herself. Got yelled at for wasting teachers' valuable time. But here is the moral to the story, that if you have something linear like this, or what Euler had, which was just, I guess, 1 plus k, or maybe just k, then what you can do is you can say that the sum is the number of pairs you have, which is half the number of numbers that you have, the number of pairs you have times the sum of the first term and the last term. So in this case, it wouldn't have been hard to do it all out. I have 5 minus 1 plus 1. I have 5 over 2 pairs. I have 2.5 pairs. That's okay. They all don't need to pair up. That middle number will be exactly half of the sum of the smallest and the biggest. My first one is what I get when I plug in a 1. I get a 13. My last one is what I get when I plug in a 9. I get a 29. Adding these things together, I believe I get 42. 5 halves of 42. Well, half of 42 is 21. 21 times 5 is 105. And that is my preferred way of doing those types of problems. Now, again, we could have done it in a number of different ways. I could have split up 4K and 9 and said, oh, the sum from 1 to 5 of 4K plus the sum from 1 to 5 of 9. And that just means I have 5 9s, so I have 45. And that 4 I could have pulled out front. So that one wouldn't have been all too hard either. But this is the way that I like to do it, and I think it's probably the most efficient way. Okay. In part C, it is not linear. I cannot use Euler's formula. But what I can do is I can split this thing up. I can say that this is equal to the sum from k equals 1 to 5 of k cubed plus the sum from k equals 1 to 5 of 3. Okay. Let's scroll backwards a little bit and look at that formula. So that k cubed formula, which is right over here, says that this should be equal to n, my ending term. So 5 times 5 plus 1, all divided by 2, and then all of that squared. And this is really just 5 3s, so it is 15. 6 divided by 2 is 3, times 5 is 15. We have 225 plus 15. I believe my answer to be 240 to this one. That wasn't altogether that crazy. Similar process for letter D. I will leave that to you guys to split up, presumably into 2 things. You could split it up into 3, but I would split it up into k squared and then a negative 4k plus 12, because that is linear and you can use Euler's formula for that one. Of course, the k squared formula for the other bit of it. Okay. Slightly different one, and we talked a little bit about this before. So in E, let's at least set it up. I am going to say that this is the sum from, how about put that 2 out front to begin with. And there's a k cubed there. Here is a k equals 4 to 24. So that is equal to 2 times the sum from k equals 1 to 24 of k cubed minus the sum from k equals 1 to, people hesitate on that, 3 of k cubed. And again, I'm going to use that same k cubed formula to figure out what that is and what that is. I believe we are more or less at the end here. On this last one, notice that it is factorable, but factoring it is probably going to be a mistake. I don't really know how to deal with different factors, but I know how to deal with different terms. So I can split this up into k from 12 to 40 of k squared minus the sum from k equals 12 to 40 of k. I don't care whether you do minus the sigma or plus a sigma, which has a negative in the argument. They'll both work out to be the same. Again, I'm going to leave this one to you guys. Please enjoy.